If you actually tried to picture Graham's number in your head, then your head would collapse to form a black hole. That's not just some sort of crazy sort of pictorial image. It would. There'd be too much. You couldn't store that much information in your head.
People think mathematicians just basically look at bigger and bigger calculations and bigger numbers, which is not entirely true, but Graham's number I love because it's the biggest number that's been used constructively.
Well, because there's a sort of maximum amount of what we call entropy that can be stored in your head. And the maximum amount of entropy you can store in your head is related to a black hole the size of your head. And the entropy of a black hole the size of your head carries less information than it would take to write out Graham's number. So the inevitability is if you started to try to write out Graham's number in your head, then your head would eventually have so much information that it would collapse to form a black hole.
If you start with a small number and 3 is a small number, what you can do is you can start adding 3 to itself. So you could do 3 plus 3 plus 3, and you keep going. In fact, what I've done here is I've multiplied 3 by 3, right? So you could just do 3 times 3. That works just as well. And if you want, you could do lots of these. You could do 3 times 3 times 3, and you can multiply it lots of times. And that that's 3 cubed.
Okay, and that's 27. So we're happy with that. I could write this another way. The way I would write this down in arrow notation would be I'd write 3 arrow 3. And that just means the same thing. 3 multiplied by itself 3 times. Hopefully you're still with me at this stage. Now I say, what's 3 double arrow 3?
You do 3 to the power of 3 to the power of 3. We would write that as, that is 3 to the power of 3.
So this means 3 arrow 3 arrow 3. Now what is it? Well, 3 arrow 3, well, I've already seen that that's 27. So 3 arrow 27. Okay. And 3 arrow 27, well, that's 3 to the power 27.
If you actually work that out, it comes out to be around about 7.6 trillion. Now at this point you can go wild, right? How many arrows do you want? So the next one, let's say we did 3 to the power of, arrow, whatever you want to call this, 3. Well, that is equivalent to 3 to the double, to the double, to the 3, to the double, to the double, that's 3 to the power of 3, to the power of 3, to the power of 3, and that stack is 7.6 trillion 3s high. And you start from the top and work your way down, and you get an almighty number. You get a number that's absolutely off the chart. You couldn't write these numbers down. You could write out of pens in the universe. But if it's 3 stacked together with 7.6 trillion, now we've got a stack of 3, 7.6 trillion of them high. And the question is, why would you want to know, right? And so actually the reason we have arrow notation is to look at very huge numbers. The famous, the quintessential, never-ending, what does end, it's finite number is Graham's number, and it's the solution to a maths problem. So in maths we do things called combinatorics, where you look at big combinations, and we look at things networks, which mathematicians call graphs, and you look at different ways of colouring in graphs. And so mathematicians looked at ways to colour in effectively graphs that are linked to higher dimensional cubes. So bear with me for all this. You can get cubes in higher dimensions and look at different ways to colour them in. And they tried to count the number of them. Okay, I've got an analogy. There's a very famous analogy for how this works. So imagine you've got a group of people. So you could have, for example, 3 people trying to have a relaxing time drinking champagne. You can then try and select committees or subsets from that group of people. You can put some people in one committee, some other people in another committee, and some people in a few committees, and there's a whole bunch of committees that you can put together. And then what you do is you say, okay, I've got all these committees, and I'm going to sort of pick pairs of committees. Okay? So I've got a bunch of pairs. Committees can form pairs, and each committee can be more than one pair, and so on. And then you say, okay, I've got all these pairs of committees. I'm going to give them a colour. Each pair is going to have a colour, blue or red. Okay? Now I ask the question. How many people do I need there to be, in the first place, to guarantee that there are at least 4 committees for which, get this right, there are 4 committees, each pair, made out of those 4 committees, has the same colour, and all people appearing, I forget, and for which each member of that committee is in an even number of committees. The ultimate question is, if I put these weird conditions on those links of matching up different committees, what's the smallest number of people required for that to be true? So, that's the question that Graham was trying to answer in a very roundabout sort of way. So he said, okay, fine, but he wasn't applying it to committees, it was now to do hypercubes in high dimensions, but it's the same question essentially. And they worked out that there is an answer, it's not infinite, and the answer is not bigger than Graham's number. And Graham's number was developed in 1971 as being the maximum possible number of people you need for this to be true. At the same time,